our meeting today. Today's speaker is Maria Belozerova with a talk devoted to dynamical systems, which are based on stochastic differential equations with interaction. Please, Maria.
Thank you. Good day. Thank you very much for the opportunity to have a talk on the seminar. Let us start with, okay, maybe I need not have full screen because as usual, it makes some problems. Sorry. As usual, as I try to do full screen, it not work. Oh, as usual, okay. Oh, now maybe you can see my screen.
No, we're just waiting for it. Okay, now it's visible.
I want to start with the stochastic differential equation with interaction that were introduced by Andrei Anatolievich Dragosov. And these are equations of type 1. And we know that it have a lot of interpretations, and one of such interpretations that are usable in different science like medicine, maybe chemistry, and so on, are the interpretation that our x from ut is a position of some particles that are moving by stochastic flow that depends of ut, and ut is in some sense a mass of ut is a probability measure that counts a mass of number of particles that I based at the set A, so mu t from A at time t. And also it can be another interpretation, but one of most usable is this one. The solution to such equations, if you consider x from R3, R plus, and omega, it is called a unique strong solution to stochastic differential equation 1 if the next three conditions are satisfied. And here the third condition gives us uniqueness in this sense that is written in formula 2. To understand the behavior of solutions, not only solutions like x from ut and also measure valued solutions ut, mathematicians do a different type of works, and one of the first results was in the paper Andrei Anatolievich Dragosov and Maria Karlikova, and there was introduced shift compactness of random measures, and that was for the goal to describe our mu t in such a way that our measures are make not a compact set, but measures mu alpha minus u alpha, where u alpha is some center measure, became compact. So it is some sense shift of our measures, and that was one of the first steps to describe the behavior of our measures on infinity. And in this paper of Andrei Anatolyevich Drogovtsev and Maria Karlikova was proved the next result. And there was considered stochastic differential equation of type 3. And it was proved the next theorem. If our starting measure mu0 has finite 2n plus 2th moment, and also if our function phi satisfies the condition 4, and b satisfies Lipschitz condition on x and mu of the type 5, then the set mu t is a shift compact. Alpha is here greater than 0, and that gives us some behavior of our function phi. This is the main condition on our phi. So later, in the works of Andrei Anatolyevich Drogovtsev and Alexander Weiss, were also considered stochastic differential equations with interaction. And in this paper, it was proved, and it was given a formula of density of our solution. And we know now that it has the type 6. So we have this formula. And to get more precise results about limit behavior of solutions to stochastic differential with interaction, there was proposed the next subsidiary assumptions on the coefficients of a stochastic differential equation. That was first of that assumption is assumption 1, and we need that our coefficients a and b satisfy the inequality 7 and also inequality 8. Also, we need assumption 2 that differentials of our a and b satisfy also the condition 2 and 3. And then by such assumptions, in the paper of Andrei Anatolyevich Drogovtsev and Alexander Weiss was proved the next theorem that by assumptions, under assumptions A1 and A2, the initial measure U0 is absolutely continuous with respect to Lebesgue measure. It opened the way to use this maybe in further investigations of our mu t. And the main result of the paper was the next one. And to introduce this result, we need the next assumption. This is assumption A5 in that paper, that if like in the paper for the Anatolyevich and Maria Karlikova, we need the condition on our function phi, that this u minus v phi from u minus phi from v is less or equal minus alpha. norm of u minus v, and by such a condition, and also we have to here a partial case that coefficient a has a special type that we see on our slide, and by such conditions we have the next result proved in the paper, that under conditions a1, a2, and this a5, we have the next lim sup p almost sure. So this is shows us the limit behavior of our solution to stochastic differential equation with interaction. From another way, in my paper, I considered ordinary differential equation with interaction, and also my goal was to investigate the behavior, but more measurable solution, because x from ut, maybe it is easier to research, but also it needs some work. It was introduced the next definition of critical points to such equation, because we have here two variables of our function f. Then I proposed to consider two types of critical points. In one case, f from x0 substituted from the first variable equals to 0, and of the type b if from the second variable it equals to 0. It occurs that the investigation behavior in the neighborhood of such points have some difference. It was proved the next theorem. In this first theorem, these cases appears to be similar. So we consider x0 a critical point of the type A or of type B of the system 9, and eigenvalues of matrix that is sum of Jacobians of such of our f from x0x, and we substitute x0, and also f from x0, and we substitute x0. And if such matrix have all eigenvalues with negative real parts, and also if for every k r k that are the differences f from x1, x2 minus these Jacobian matrices and x minus x0 satisfy the condition 12. And then for sufficiently small m1 and m2, we have such limit. So this nonlinear part don't make problems to behavior of our moment of mu t. And this also helps me to have another results. And here the researching of critical points of different types became some differences. And here, in case of critical points of type B, we need such conditions to our nonlinear parts, that the first one equals just to 0, and the second depends only from x2, and for sufficiently small supremum, we get the next result, that the mu t tends to such a measure in Wasserstein distance. In another case, for critical points of type A, we needed another conditions of our nonlinear additions R1 and R2 of the type 14, and the final result in this case is also different, but our mu-t tends to delta measure in Wasserstein distance. And of course, all these results work in case of linear system. And the idea to get that's all, of course, was in if our F just constant matrix was, and then it was made from general case of nonlinear. But the main problem is to have good results for stochastic differential equation with interaction. But also, I want to recall some facts about ordinary differential equation to give understanding what exactly we can wait and in what direction maybe I will work. Let's consider dynamical system defined by ordinary differential equation and the traditional critical point at just x0 if f from x0 equals to 0. And then in theory of ordinary differential equation, we have a knowledge about cycle or periodic orbit. If any solution curve is not a critical point or equilibrium point and is such that our solution phi from t plus t equals phi from t. And then we say that we have a periodic orbit or cycle. And this knowledge are today introduced to dynamical systems on manifolds. And let us consider differentiable manifold, and let's consider vector field on this manifold, and a map X, and let us consider equation that produce dynamical system on the manifold. This is alpha derivative equals this x from alpha, and then we also have a knowledge what is the orbit. This is the image of an integral curve, and this image is on our manifold. And then for this case, in theory of ordinary differential equations and dynamical system, so we have the next results that let us denote omega from pi. This is if we have some pi, omega from pi is a omega limit set from pi that is a set of points, and that limit that our dynamical system moves as t. This is a limit set of our p moved by flow of dynamical system. And the next theorem gives us knowledge what can be this limit set. And first we know that it is non-empty, closed, and invariant by the flow. And here, in this case, if there are dynamical systems on manifold, that just means that it's a union of orbits or just critical points. And also know that omega from pi is connected. Also, in the next theorem will be alpha from pi. The difference is the next one. If that omega from pi, we take a limit as t tends to plus infinity, and alpha from pi, we take a limit as t tends to minus infinity. And let me recall the well-known theorem about the behavior of these limit sets on sphere S2, well-known Poincare-Bendixson theorem, that the result is the next one, that in this case, our omega from P or is a singularity, critical point just, or it's a closed orbit, or consists of singularities and regular orbits that in some sense tends to this singular point. To understand better the situation, I propose to look on some pictures. So it can be different situation, and we have it can be just a spiral trajectory that tends to a critical point, or it can be some cycles in the neighborhood of critical points of, or more complicated structure like in the first picture. But the main goal is that all limit sets on still are described by that theorem. So the idea is to make something like this about dynamical systems drawn by stochastic differential equations with interaction. To do this, we firstly need to understand what is a random dynamical system. So what a deal can we make with this randomness? And this knowledge is described for today. We can consider a book of monograph of Ludwig Arnold, and there was a definition of random dynamical system. And what is here? Let me have a probability space, and let us call pair of mappings theta phi a random dynamical system if the next conditions are satisfied. First conditions of theta, that is, it's a metric dynamical system, and conditions on phi is such that if we make this, we consider phi from t plus s omega, then we have the next one that equals here phi from t, but here we have theta s from omega, and here phi, the previous one from s omega. Then, if such conditions are satisfied, we call this pair random dynamical system. And for stochastic differential equation, ordinary stochastic differential equations without interaction, there is a lot of results about Stratonovich stochastic differential equation, but also in book of Ludwig Arnold, I found the result about Ito differential equation of the nest type that by the conditions of our phi e, we have that this equation made a continuous random dynamical system phi. Our filtered dynamical system describing Brownian motion. And this phi solves this stochastic differential equation. My goal was to consider stochastic differential equations on manifold. And to start this, we need a paper of Andrei Anatольевich Dragosov and Alexander Weiss. The next one, and then this paper was described and introduced what is a stochastic differential equation with interaction on the d-dimensional Riemannian manifold. So it is an equation of type 16, and also there was introduced what is solution to such equation, that for every phi in C infinity, we need that it satisfies such an equation in integral form. Also in that paper were get Krylov-Vertennikov composition and other results. Now my goal was to do something on manifold and to get some results about behavior of match value solution. So first I propose to consider very simple linear case to understand what situations can be. Let us consider equation 17. And let us notice that if we start in some point, but here we have x, here it has to be x from ut. If we start in some point, then because of specific of the system, we will move on the sphere with the center in 0, because the differential of the sum of square equal to 0. So this is a system on S2, on the sphere S2. And the next good news is that we can easily solve this system, and also we can check what are here critical points in usual sense, just zeros of our right part, and then these are points of type t minus t for every t in R. So after solving the system, we can also understand the behavior of our critical points. Because of type of our solutions, we get that integral curve in every time lies not only on our sphere S2, but on the plane AT. Therefore, we understand the behavior, because if we consider our sphere and if we start to move in some point, that we understand that we have to be on that plane, because if we have a fixed integral point curve, then we have C1 at a constant. then we have to be always on the plane, and then therefore we have to move just on the circle. This is our behavior of integral curves in this case. Also, what then we get about the solution ut. So we can rewrite our solution x from ut by just a rotation tt u, and then we understand if we put initial measure u0 like a delta measure, then we just will rotate, and mu t equals also delta measure tt from u0. And in another case, if initial measure is uniformly distributed on our sphere, then it will just rotate, and we get that ut is also uniformly distributed on S2. So we just have an example what can happen. But my goal was to do something in general case. In the first step in this direction was the next one. I considered stochastic differential equation with interaction of type 19 on some compact smooth connected d-dimensional manifold. And I propose the next definition of a random dynamical system depending from measure, because here we have dependence from ut, from u0, and also from ut. So I propose the next one, that in our formula 20 we have that our dynamical system, if we have here mu t plus s, then this is phi, and here we have mu t from also theta s from omega, theta s omega. Of course, in partial case, if we have not dependence on free t, it's just usual definition of random dynamical system. And then I get the next result, that if I have stochastic differential equation on manifold, then by that conditions A1 and A2, we get that there exists a measurable function phi such that for theta t that equals w from t plus point minus w from t, the our phi is a random dynamical system depending from measure mu0, of course, mu t, tan t, and so on. And let us prove this result. Firstly, let us recall that in the book of Drentovich-Dragotsev, it was proved that solution to stochastic differential equation with interaction gives us a version of solutions that is a stochastic flow of diffeomorphism, as our S is fixed. And then we have the next formula that gives us this flow of diffeomorphisms. And now, if we look of the definition of dynamical system depending from measure, we look that to prove the theorem, we just need to prove formula 22. And this formula I propose to prove using approximations of solution to Cauchy problem. I consider two Cauchy problems for first one that starts from S, and here we have initial measure mu S, and the second one that starts from 0, and there we have initial measure mu 0. Then I wrote that's all formulas, and then I will prove by induction the next statement, that if I put my theta s, then I get exactly x as k, and with that dependence of measure that I wrote in previous slide. Then I suppose that it is correct for k, and then by induction I have to prove that it's also true for k plus 1. Here we can see the formula for our xk plus 1, and then we see that we can use induction hypothesis here, and we can just take for k the next formulas and substitute into formula for xk plus 1, and then I have the next one, and then the formula is proved, and therefore we have our results for the whole theorem. So we have a dynamical system, but then after that my idea was to get something like cycles, like limit set and so on. And the first idea was the next one. Again, consider ordinary differential equation with interaction, and to do the next one. We have first step was consider this system on the sphere S2, and suppose that we have ordinary differential equation on sphere S2, then we also have one opportunity that we have some cycle, one cycle in this case, gamma, and some critical points. So in this situation, we understand that our integral curves behaves like on the picture. So we have some critical points, and this all integral curves tend to our limit cycle gamma. So for sufficiently big T, we know that every set A that is not in the epsilon neighborhood of our gamma, there will be no points of that starts in some set on sphere, and then our mu t from this set will be 0. So it gives us the result of the lemma, so of every such set A for sufficiently big T greater or equal to 0, we have that T from A equals 0. And then the next idea was to make from this equation system stochastic differential equation with interaction stochastic. The idea was also from book of Ferdinand Drogotsov. We can make time change. So we consider this integral, and we consider this tau and mu t, and then we have that for this y, we get stochastic, not stochastic, but ordinary differential equation with interaction, with dependence of this new t. But the next important thing is that our trajectories are the same because we has only time change. So our trajectories are the same. And then this result about that our mu from A equals 0 for sufficiently big T is also true, but this T will be random. And then we get the next result that we can then find just that T0 such that our mu T from A equals 0. But it's just starting ideas, and my goal is to do something more precise and more general, maybe. Also, I propose to consider the next literature because they help me a lot by my work, and this is classical books of this dynamical systems and stochastic dynamical, random dynamical system, and so on. And that was all that I wanted to say, and thank you very much for your attention.
Okay, thank you very much for interesting talk. And maybe someone have questions or comments, please. Let me have some small comment. We are working with Maria in the following direction. We are trying to find the situation when we can move the finite dimensional situation, namely the total complete description of the limiting behavior of trajectories of solution to ordinary differential equation, like Poincare-Bendixson theorem, to infinitely dimensional case, because we know that the space of measures, even in case when we discuss the compact manifold, the space of measures is infinitely dimensional. Still, the statements which was proposed by Maria shows us that at least in some cases we can expect that the behavior of these measure value solutions to equation with interaction will inherit some properties of trajectories of ordinary differential equations on the compact manifold. This is the idea, and I hope we will be successful to get the analog of Poincare-Bendixson theorem for such lemma, for such situation. Maybe some other questions, please.
I wanted to ask about shift compactness. Is it relative compactness of shifts?
It is compactness of the family of measures, and sometimes it is called relative compactness, or sometimes compact in space of measures, which respect to Wasserstein distance of zero order. It is the same. So we just have to find for any measure such element that we shift the measure on this element u alpha and get the compact family. In case if we consider the measures which have a finite moment, then the conditions or description of compactness is slightly stronger than usual compactness of measures in the sense of V convergence. For example, if n is greater or equal than 1, it can be checked that if the set mu alpha is shift compact, then one can take as shifts u alpha the means of these measures, the first moment. But this theorem also can be, this property also can be investigated for measures which has no any, which has no.
So all these shifts form a closed set in vector topology.
The situation is totally different. And by the way, I think Kirill Kuchinsky last week showed us the example of a linear equation with interaction, which has exactly the following property. The mean of the measure floats around the space like Brownian motion, and in dimension, in any dimension, it is not a compact trajectory, yeah? But the measure is concentrated near this mean. It does not spread over all space. So this notion was invented to reflect exactly such situation, where we can move measures along the space, but measures cannot spread a lot.
Do you work with extrinsic description? So you embed manifold in some Euclidean space, and then solutions live in the embedded space.
You see, when we with Alexander Weiss tried to prove Krylov-Vertennikov expansion, in one time we use the embedding into Euclidean space of our manifold, and even we use the extension of the coefficients on this Euclidean space in order to use some linear structure. Yes, sometimes it is useful.
But here in this talk, X, dimension of X was dimensional manifold or dimensional embedded.
Yeah, we just have a manifold and it is enough.
But in the proof, there were additions used, right, of integrals.
Yes.
So how do you have on a manifold if it is not embedded?
Maria, can you please demonstrate our system, our theorem with Weiss? Yes, and maybe the next one. This integrals.
Yes.
It is interesting. Here is a nice definition of the solution to the equation with interaction. But by the way, it is not necessary to say that this is equation with interaction. We just define the family of
yes, that's I understand. No, that's I understand. Yes. That's perfect. Yes.
We move functions. Yeah.
But if you go to the proof where there was iterations used later on,
we consider, I think, here, yes, here.
Yeah. So in this proof,
also, you can avoid also this embedding, but you see, the result will be the same. It does not depend. Do you use it or not? Yeah.
Well, I think that, well, usually approximations, because that's an approximation, it will leave the manifold.
Yes.
So if it is intrinsic description, then B will be geodesic. Well, related, not geodesic, related to the metric. It will be metric.
Here, I think Maria use embedding here.
Okay. If it's embedding, okay. But still, even if it is embedding, this X, these approximations, they most likely will leave the manifold.
Yes,
Because you're
it can
freezing the
move, but
coefficient and Brownian motion moves.
exactly. But we have a convergence to the solution. We have such statement. So
But the coefficients needs to be extended, right?
yes,
Okay.
exactly, exactly.
Okay.
We
Thanks.
did such extension in our
Yes,
paper.
yes, of
With
course.
IC.
Yes. Thank you.
You're welcome. Okay, other questions, please. If there are no other questions, then I have two announcements. The first announcement is that we end our semester, and the next session of in such format of our seminar will be organized in the beginning of the September. So please, during a summer, send to Katerina your proposition with your talks, if you have one. This is the first announcement. Second is that despite of this, next week we have even extended a session of our seminar, which we call Skorohod Readings. This is a mini conference for young persons who just make his or her first steps in investigation, probability, and random processes. And this conference will held 2 days, Monday and Tuesday, June 8 and June 9, from, I think, from 16 to 19 every Kiev time every day, and the announcement will be sent tomorrow as usual. Please follow the link to participate, and I hope that we will have some interesting talk on this conference. And the last one, also for all participants of the seminar, I kindly invite you, especially those of you who make a talk during the semester, to send papers with devoted to the subject of your talks to our journal, Theory of Stochastic Processes. Official letter with invitation you will get from our secretary of the seminar. That's all. So see you next week. Bye.
Thank you. Bye.